Hello everyone, I hope you all are doing well. So in the previous sessions, I had covered the basics of CAE/FEA part 1 to 6. Okay, so here I'm with the part 7. In this session, I'll be covering the failure theories in depth, how exactly them to consider for ductile as well as brittle materials. Okay, a few things with respect to Abaqus, hypermesh as well as Ansys. So which and all the failure models the softwares will consider to deal with this particular failure criteria, and what exactly this hourglass and shear locking and volumetric lockings and all. So these things will be covering in this particular session. Okay, let's get started with this. Yep, so as we already know, when it comes to the structural analysis in FEM and CAE domain, we have the two main types. One is the linear and second one is the non-linear. When it comes to linear, we have the linear static analysis and the linear dynamic analysis. Okay, so in linear dynamic analysis we have seen that is the frequency based, that is model analysis. Okay, and then harmonic, then we have the random vibration analysis. Okay, and then earthquake analysis we can consider. These things will be there in the linear dynamic analysis. Now when we move to the non-linear zone, so we'll be having the two main divisions, that is implicit non-linear and explicit non-linear. So taking these non-linearities, that is material non-linearity, geometric non-linearity, contact non-linearity into account, will be solving them. Okay, so as I already explained what is implicit and explicit in depth before, so for example, for implicit analysis we are going to solve the solutions for static analysis. Okay, for explicit we'll be dealing with the crash drop test and the explosion bird strike analysis and all. In static strength, in the sense we'll be dealing with the plastic region. So okay, we'll be just coming out of the elastic region and we'll see how exactly the plastic region will behave in this implicit analysis. Okay, well, so you can see this particular image here. We have the exact explanation for the what is implicit method and the explicit method, where exactly the static and dynamic analysis will be differentiated, and about the quasi-static as well. So when it comes to implicit analysis, so this is the example. Okay, the loading condition. So we'll be dealing with the structural problem in the static analysis, right? When it comes to the quasi-static, we'll be dealing with the same static analysis and we are going to take this one into the plastic region. So if you consider the punch and die effect, so this is the complete deformation is going to take place for this sheet metal component, right? So this metal forming will come under quasi-static analysis. Okay, when it comes to dynamic analysis, so impact problems like the drop test, the crash analysis, okay, the sudden impacts will be considered into this dynamic analysis. Okay, I hope you got this particular differentiation between the implicit, explicit and the quasi-static analysis. Okay, well, so this is the graphical represent for the dynamic analysis and the quasi-static, where the quasi-static is used to represent the slow dynamic process for the dynamic process. Okay, so here it is the fast in one shot dynamic analysis. Okay, here it is, it will start gradually and then it will move with the dynamic region. Okay, now what are the stages in the FE analysis? So we have already gone through this particular things before, but here I'll explain in brief, okay, what and all things will happen. So first thing, we need the input information, right? The geometrical data, in the sense what and all, like the number of elements, nodal points, right? the element types which we are going to consider, isn't it? And then the coordinates of each node, and then we have the connectivity for that nodal points. These things we're gonna define it in the geometric data. When it comes to loading data, what and all things we need to define there? So we need to define the loading conditions like the pressure or the force which we are going to apply, what is the magnitude we are going to apply, whether it is on surface or a point. So these things we need to define it in the loading data. Next thing, the material properties. So which material we are going to assign, right? So the material properties for the static analysis, what and all we need to define, and the nonlinear analysis, what and all things we need to take into account, what and all the failure theories we need to take into account, right? So like Young's modulus, Poisson's ratio for the static analysis, isn't it? So like this, the material properties also we need it for input information. Next thing, whatever the things you want to specify, after that we need to define the boundary conditions, right? Where it is fixed, whether it is something related to crash analysis or impact analysis or the drop test, the fatigue or whatever it is. So we need to define the boundary conditions, okay? Specified displacement, whether it is there or not, everything we need to check with respect to boundary conditions. Now for these all the things, the Gaussian points will be created for each and every element, okay? Well, so once you give these all the inputs, what exactly happens in the pre-processing stage? So we know, right, the stages in the FEA, one is pre-processing, processing, and the post-processing. Now in the pre-processing, whatever the input data we have given, right, so that will be processed completely. So what exactly happens there? It will start with the initializing the global stiffness matrix and the load matrix which we have defined for the cost points. Okay, so now what exactly happens there? From these global stiffness matrix, so it will start uh, trying to assemble all the elemental stiffness matrix, and then the elemental stiffness matrix is initialized. After that, what happens? So for these all the numerical integrations, so the Gaussian point will be created, right? So for these all the Gaussian points, so the how exactly this stiffness matrix is going to be contributed will be found, okay? And then after that, it will start defining the shape functions, okay, for each and every Jacobian matrix. So it will find the determinants, okay? So next thing, once this all the Gauss loop is completed, so what happens there? So the global stiffness matrix is available, right? It will solve for each and every Gaussian points, and it will give you the global stiffness matrix. So now, so using whatever the loading data which we have given, so and whatever the nodal values we have initialized now, that it will take into account, and it will solve for the uh, boundary conditions. Okay, so these boundary conditions will be solved with respect to the penalty method. Okay, now so whatever the things you have defined it in the pre-processing stage using the standard solution packages like the radios, OptiStruct, LS-Dyna, Abaqus. Okay, so even the Ansys solvers use the standard packages, and then it will solve for the variables at each and every cost point, okay, like the stress, strains, and the uh, global cost points. Okay, it will solve for the stress, strains results for each and every nodal variables. So once it uh, completes, it will go with the post processing stage. So there what happens, whatever the results you have extracted from the processing stage will be viewed, and you can able to check each and every results like stress, displacement, strains, and all by using the post processing so like the tools. This is the complete flow chart, how exactly the simulation will start, what and all the things it will take as an input, and then how it will initialize, and then uh, pre-process and the processing stage and the post-processing things. Okay, so you can refer it later. Now we'll see the failure theories in depth. Now here, when it comes to failure theories, we know, right, there are some engineering materials are available, like the metals, plastics, glass, concrete. These things will be there in the real life. Okay, so how they gonna fail, right? Due to the fatigue, right, due to corrosion, erosion, stress, cracking, right? So due to these things, the strength of these all the metals or the materials will fail. So for these all the materials, we have the different failure criteria. So for ductile materials, for the brittle materials, we have the different failure criteria we need to consider. We'll see these things. Now when it comes to ductile materials, okay, here, so these particular ductile materials will fail when the metals undergoes the substantial deformation before the fracture. So it has some deformation. There is a huge plastic deformation. So we have seen, right, the stress strain curve for the ductile material, and even we can see the necking formation due to the Poisson's ratio before the material failure. This will happen in the ductile failure. When it comes to brittle failure, what exactly happens for the materials like plastic, concrete, glass, composites and all? So it will undergo sudden fracture, sudden failure. There is no much noticeable deformations in it. Okay, very small, or there won't be any deformation. You need to remember that. So in short, uh, for the ductile material, so uniaxial stress reaches the yield strength. Okay, now here in the brittle material, whatever the ultimate strength is there, directly it will take the failure criteria. When it reaches the ultimate stress, the brittle materials will fail. Now we'll see in depth about these all the failure theories. So when it comes to ductile materials, we have the Tresca criteria, we have the von Mises, that is maximum distortion energy, Hofsford, and the Gerson failure criteria. Now we'll see how exactly these things are, and what these criteria are showing us to do, and what exactly the inputs are there in it. When it comes to the Tresca criteria, that is known as the maximum shear stress theory, what happens here is the failure occurs in a material due to maximum shear stress. Okay, this how exactly it is. So let's say we have the yield point, so it should reach the maximum shear stress. So yield, whatever the yield point is there, that should be due to the maximum shear stress. So in short, the yield strength will be the maximum shear stress there. Due to that, the ductile material will fail here in the Tresca criteria. Okay, so in this theory, whatever the hydrostatic stresses are there, we won't consider them. So what is hydrostatic stress? So only the uniaxial stresses, not the shear stress. So you need to remember, this Tresca criteria is used to solve the plane stresses, the 2D membranes. If you are taking, so you are considering the plane stress, we use it Tresca criteria. Okay, shear stress. Now next thing is to deal with the von Mises yield criteria. There the maximum distortion energy takes place. So here what happens is, so the failure occurs in a material due to the maximum distortion energy. So at exactly the yield point, it should be a maximum distortion energy. Okay, the failure due to the shear stresses, okay, present in the model. So that can be calculated by using this formula. Okay, that is sigma 1 minus sigma 2 whole square, sigma 2 minus sigma 3 whole square, plus sigma 1 minus sigma 3 whole square by 2, 1 by 2 in the sense square root of this, which is equal to sigma y. Okay, this is how it's gonna find out this principal stress here. Okay, so this is for maximum distortion theory. So of the failure will happen due to the shear stresses, so that will be represented in the form of the principal stresses. And you need to remember one more thing, whatever the Tresca theory is there, Tresca criterion will be uh, en, uh, en, encom encompassed by the von Mises yield surface. In the sense, you could able to see whatever this Tresca criteria is there, it is well fitted into the von Mises criteria itself. So we can even consider the von Mises criteria for solving the Tresca criteria as well. So that is we can consider, but if you want to consider the plane stress, you can even directly choose this maximum shear stress as well, or you can even consider the von Mises yield criteria as well. So both are okay. So this is under the elastic limits, okay, and even you can consider the plastic limits here onwards, the Hofsford yield criterion. So here this particular failure criterion is defined for the plastic deformation, as I said, okay, material under the triaxial stressing state. So there uniaxial, here it is triaxial state as well. Okay, the formula you can see it is same as that of the von Mises criterion. So there 1 by a is here, instead of square root we have the whole square of a here as well, sigma y, where a is 1 or 2. When it comes to 1, so it will be a stress criterion, and it comes to 2, it is von Mises yield criteria. So we can consider Hofsford yield criteria for all the kinds of analysis when it comes to plastic deformation, even the static analysis and all. So by default you can even select the von Mises criteria, or else in advanced thing you can select the Hofsford yield criteria. Now this one, the Gerson failure criteria, it even consider the von Mises criteria into account as well. So this is compatible for the ductile plastic porous solids in general. So porous in the sense the material which has the hyperelastic properties, okay, that we can consider here. So these are the few explanation for these things, the formulas and all, you can refer it, but it's gonna even refer the von Mises yield parameter as well. So maximum we're gonna use Hofsford or the von Mises criteria, remember that for the ductile materials. Now when it comes to failure theories for brittle materials, we have the Rankine failure theory, that is known as the maximum principal stress theory. Here again we have the Coulomb Moore failure criteria and modified Moore criteria. We'll see what exactly these things. When it comes to the brittle materials, we know that the failure due to what? The fracture, not due to the yielding, not with the necking. Okay, so here the compressive loading as well as the tensile strength comes into account. So due to this they will fail. Okay, so this particular theory should deal with the tension as well as compression to get the failure analysis. So now when it comes to Rankine failure theory, so what it assumes, the material failure occurs when the maximum and minimum principal stresses reaches the failure strength. Okay, whatever the principal stress is there, if it reaches the failure strength, in the sense the ultimate stress, the component will fail. Directly it will fail. There is no shear or whatever it is, there is no necking and all. Okay, no plastic region, directly failure like that. Okay, so what exactly here happens is it is only considers the principal stress, that is very important. Okay, it is not applicable for ductile metals, we already know why it is, right? Now this is for brittle material. Now when it comes to Coulomb's Moore failure criteria, what happens here is, so this theory consists of hydrostatic stress also into account, that is axial stress as well as the shear stress. Both compressive as well as tensile loadings are taken into account. Okay, assumes that the plane of maximum and minimum stresses contains the normal plane to the failure. So this is the mathematical expression for this, and this is the graph, and this is the nonlinear region. Okay, now so even the tension and compression will be taken into account. So with respect to that, how exactly the maximum principal stress is distributed here. Okay, that is plane stress. Now next thing is the modified Moore failure criteria. So why it is taken into account instead of only the Moore Coulomb's criteria? So whatever the Coulomb-Moore theory is there, no, it does not agree well for all the experimental data. So some modifications has been proposed into this modified Moore criteria. So like for soils and all, okay, different types of soils we can consider. So what exactly here happens is the it captures the pressure dependent shear strength and irrecoverable compaction and the non-linear elastic unloading in the brittle materials. Even unloading also it will consider, we have seen, right? So the formula, there are some modifications into it, and you could see the yield surface here. The Coulomb's Moore theory is this. Okay, this considers this modified Coulomb's theory is this. Okay, the complete one. Normal stress even, this one, the normal stress for uneven materials. Okay, so this is the complete explanation for all the brittle material failure theories. When it comes to hypermesh, we consider these cards. Okay, so like we have the cards for ductile materials, composites, metals, fibers, metal formings, and all. So when it comes to ductile materials, the Johnson Cook model we consider, okay, maximum. So this particular Johnson Cook model is very famous. Even it is under in Ansys as well as Abaqus. So if you are going to deal with the failure due to the ductile, like failure for the ductile material, we consider the Johnson Cook model. Okay, we can even consider the biquad card for ductile materials. Okay, so for composite we have this Chang, where is it? So here, okay, Chang. Well, so like that we have the different cards for each and every analysis. So when it comes to one more, I would like to represent uh, that is for this one, the sparling and the ductile materials. We have this again, Johnson Cook plus sparling. Okay, for fatigue failure we have this Butcher model. So T Butcher will be the card for fatigue analysis inside the hypermesh. Now when it comes to Abaqus, so when you are going to deal with the ductile damage, we have the Johnson Cook damage model. So for the different models like the brittle materials and all, we have this cast iron plasticity model directly, clay plasticity model. So CDP, that is concrete damaged plasticity. Okay, and again we have the Drucker Frager Morse column plasticity model, porous metal plasticity, creep, swelling, viscous. These all the things would be there. Okay, now we have some explanation for these all the things you can refer. When it comes to porous elasticity, the components like polymer and the crushable foams will be analyzed with this model, so very advanced. When it comes to CAM clay, so it will be used to deal with the soil decomposition and all. So here all the yield surface, flow rule, and the hardening rule will be taken into account. Drucker Frager, again it will be used for the same thing, okay, to deal with the different types of concrete and soil elements. Okay, now same thing again, the Moore column criteria assumes the failure is controlled by the maximum shear stress, and this shear stress depends on the normal stress whatever we are going to apply. Okay, well, so this is with respect to Abaqus. Now when it comes to Ansys, Again, for the ductile material, it will take the Johnson Cook, simplified Johnson Cook we have. So when it comes to the durability analysis, the fatigue, it will consider the power law plasticity into account. Okay, well, so Ansys workbench, whatever we are using, normal one, so it doesn't deal with this fracture problems because it has some drawbacks in it. Okay, it doesn't have that material elimination element elimination method into it, so it will use the default algorithm, that is kx is equal to f in Ansys. Okay, so it cannot affect for the fracture, we already know that. So in explicit algorithm like LSTENA and some of the APDL scripting can help us to deal with this explicit analysis inside the Ansys that we already know. Okay, yep, so that's all about this particular Ansys failure criterias which we'll consider. Now this hourglass effect, shear locking and the volumetric locking, what is it? When it comes to hourglassing, so this will occur in first order elements. Okay, so reduced integration like C3D8, the tetrahedral element, right? First order, it is not tetrahedral element, it's the hexahedral element C3D8. So what happens exactly here is, so it has only one node at the center, integral point into integration. Okay, so it won't help us to deform, can say this change, no, the element will not deform like this and it won't have this angular deformation as well. So due to this, the material become too stiff. Okay, highly spurious results. Okay, so it won't deform as we expect. So due to this, the hourglassing issues will happen inside the model. So to avoid this, so we have this second order elements we can consider, that is C3D20R hexahedral second order elements. Okay, reduced integration, we can even consider that. Well, so when it comes to shear locking, so what happens here is, so if we consider this particular model, so again it will occur for the first order elements. If we consider C3D8, okay, subjected to bending, so when artificial strain develops due to the instability of the element undergoes to bend, so there are some points will be created inside, right, the integrated element. So these points, so what happens here is, they won't allow it to again bend, deform. So this results in a non-physical shear strain. Okay, this element can be two-step due to this. Okay, so due to that, shear locking will happen. Now again, this, if you want to avoid the shear locking as well, so we can use the second order element, that is C3D20, as I said. So volumetric locking, in the sense the components they won't like, you can consider incompressible property, let's say kind of rubber and all. So volumetric locking will happen for both first order and second order fully integrated elements. Okay, this causes the unrealistic pressure stresses to develop at the integration point, in the sense whatever the elements you're going to consider, no, they're completely incompressible. Okay, so to avoid these things, so we have the hybrid element formulation to deal with these things. So let us see them. So you can see when it comes to, we have the incompatible mode 8 node brick element, that is C3D8I. So here we have the improved performance for these things. Okay, so here the shear locking is removed and the volumetric locking is also reduced. Okay, so we can use this particular incompatible mode 8 lock C3D8 to avoid these issues as well. So again, so when it comes to reduced integration elements, so we have seen there is 32% of variation in the results, so we can't use due to the hourglassing effect inside the C3D8 reduced uh, integration elements. When it comes to fully integrated C3D8 directly, the first order element, there also you will face this what it is, shear locking. Okay, there also you have the 34.5% deflection, so it is too much. So to avoid these things, we have the incompatible mode of C3D8I integrated. So here improved accuracy will be taken into account for the bending dominant problems. When it comes to bending moment, okay, remember that. So in that cases, we can just avoid the C3D8 and C3D8R reduced integration. We can consider the incompatible C3D8I, or else we can even use the second order elements like C3D20, C3D20R. Okay, so generally this is the accuracy wise. C3D20 has the better accuracy considered C3D8R. Okay, C3D20, C3D8 more than that, again C3D8R, C3D8. So this is the explanation for shear locking, hourglassing effect, and the one more is the volumetric locking. Okay, yep. So when it comes to the non-linear analysis for the uh, steel components or ductile materials, we can take the isometric elasticity and the kinematic hardening and the dynamic hardening into account. These are the values we can consider for the structural steel. For brittle material like the gray cast iron, we can consider these material properties. In future we can refer them. Okay, for your reference you can just have it. Okay, yep. So that's all about this session. I hope you got to know about failure theories, how exactly the software are going to utilize these things to solve the explicit analysis. Okay, so it is just not complete details which I have provided. Whatever the knowledge I have grabbed from the internet, I could able to deliver it. That's all. So if you want to learn more about it, you can research on the research papers, or you can refer the Ansys, Abaqus, and HiFoMesh websites, so to get the more details on the same thing. So if you feel like if you want to add few more details into it, or if you want to just let us know what and all things should be added in the upcoming sessions, or what and all things should be corrected in the previous sessions, you can comment in the comment box once we upload these all the videos and all. So your support matters. Well, that's all about the session. Thank you guys, stay tuned. Bye everyone.